Okay, so next we're going to be talking about how to factor polynomials. So these higher degree polynomials, we've already factored quadratics, right? Things with x squared in them a bunch. But now we're going to be talking about factoring higher degree polynomials. Some of them will be quadratics, but we might see cubics or quartics or quintics, etc. Those big high degree functions. All right, so our first step anytime we're factoring a polynomial is we always factor out the greatest common factor first. So always look for a greatest common factor. And then we're going to kind of break it down by how many terms we have in our polynomial. So we'll have some tools if there are 2 terms, 3 terms, or 4 terms. If there's more than that, or we can't get them to kind of fit these different forms, then we're going to have to try some other approaches that sometimes take a lot of time. So these are really nice when we get to use them. Okay, so let's say I only have 2 terms. The first thing we're going to look for is that factoring pattern we've seen before called the difference of squares. And that's where we have these things called conjugates, like a plus b times a minus b. So if I have 2 things that are perfect squares, a squared minus, remember that's the mathematical word for difference is subtraction, so minus b squared. It will factor as a plus b times a minus b. So let's take a look at this first examples. We have 2 terms, and our first term is a perfect square. And so we're going to label it a, and what times itself twice is 4x squared. That ends up being 2x times 2x. Okay, so my a value is 2x, that's what's squared. The minus is part of the formula here, so I don't need to worry about the sign. I'm just looking at the 81. What times itself twice is 81? And of course that's 9, so that's my b value. That's supposed to be a b. Okay, so if we follow our pattern, it factors as a plus b, 2x plus 9, times a minus b, which is 2x minus 9. And you can always check by foiling these together, but you do get back to 4x squared minus 81. The middle terms cancel out. That's what always happens with our conjugates. And there's our factors. Okay, let's take a look at our next one. 50 isn't really a perfect square, and either is 18. So it feels like I'm kind of stuck, like it really doesn't fit the difference of squares. Until I come back and remember, I always want to take out a greatest common factor. So if we do that first, they're both even numbers, so I'm pretty sure I can divide a 2 out of both terms. So we're going to factor this 2 out, and dividing each by 2, I get 25x squared minus 9. And now 25 and 9 are both perfect squares, and of course so is x squared. And so now this fits my pattern, where my a value inside of my parentheses here is what times itself twice is 25x squared? Well, that's 5x. And my b value, what times itself twice is 9, is 3. So I'm going to keep this 2 that we factored on the outside, and then we're going to factor our difference of squares, which is 5x plus 3 and 5x minus 3. And there's our answer. 5x plus 3 times 5x minus 3 times the 2 we factored out earlier. Okay, next we're going to talk about the sum and difference of cubes. Okay, there is no sum of squares. If you see something like this, x squared plus 4, this does not factor. Okay, there is no sum of squares. That is not a factorable pattern. At least not with integers or rational numbers. Okay, but we are going to look at cubes, and so you probably haven't worked much with cubes, so we need to identify what numbers are perfect cubes. So let's take a look at some of them. So I wrote a little list over here. We'll only really need to know up to about 7. So 1 cubed, 1 times 1 times 1. Well, that one's easy, it's just 1. 2 times 2 times 2. Let's see, 2 times 2 is 4, times 2 again is 8. 3 cubed. 3 times 3 is 9. Times 3 again is 27. 4 times 4 is 16. Times 4 again ends up being 64. 5 times 5 is 25. Times 5, if you have 5 quarters, that's $1.25, so 125. 6 times 6 is 36. Times 6 again ends up being 216. And 7 times 7 is 49. Times 7 again ends up being 343. So you probably haven't seen these numbers a whole lot, but these are perfect cubes. And so if you end up seeing them, hopefully you're thinking in your head that that's a cube. And if we have 2 terms, maybe it fits this sum or difference of cubes pattern. Okay, and the nice thing is they're actually very, very similar if you look in their setups. The difference of cubes is a minus b times a squared plus ab plus b squared. And if you look at the sum of cubes, it's almost identical. There's only 2 differences. When it's the difference of cubes, this first term has subtraction in it. When it's the sum of cubes, the first term has addition in it. So there's one difference there, it's just the sign. The only other difference in this second term is this sign of the middle term. When it's the difference, it's plus AB. When it's the sum, it's minus AB. Otherwise, they're identical. So it's really just a couple sign differences here and here. So let's try these out. Okay, so we just discovered 27 is a perfect cube, and of course x cubed is a perfect cube. So let's identify our values. What times itself 3 times is x cubed? That's x, that's my a value. And again, the minus part is, or the minus sign is part of the formula. So what times itself 3 times is 27? Well, we just discovered that's 3. So b is 3. Okay, so following my pattern, this factors as a minus b, x minus 3, times a squared, x times itself twice, x times itself twice, x times x is x squared, plus a times b, x times 3 is 3x, plus b squared, so 3 times itself twice is 9. Okay, and I can tell you this quadratic at the end is never factorable. So you don't have to waste your time trying to break it down further. It does not factor out to nice whole numbers. You either get imaginary solutions from that or irrational answers, but it does not factor. Okay, so let's try this with the sum of cubes. Remember, there is no sum of squares, but there is a sum for cubes. So let's identify my a value. What times itself 3 times is 8x cubed. Well, that ends up being, we know that 8 is 2 cubed, so this is 2, and x times itself 3 times would give me x cubed. So my a value is 2x. 2x times 2x times 2x would give me 8x cubed. And b, 125 is 5 cubed. So my b value is 5. Okay, so following this pattern, I'll write it down here a little bit. We have a plus b, 2x plus 5, times a squared, 2x times itself twice. So 2x times 2x is 4x squared, minus a times b, so I'm just putting the minus, it's part of the formula. 2x times 5 is 10x, plus b squared. So plus 5 times itself twice is 25. And again, this quadratic does not factor out further. You don't have to waste your time trying. There are many mathematical proofs proving why that's true. Don't worry about going through those, but just know that you don't need to waste your time there. Okay, let's check out our next examples. So what if I have 3 terms? Okay, if it's 3 terms, hopefully it's a quadratic, like a normal quadratic we've been factoring before, and we can factor those out like we've been practicing. But sometimes we do get a higher degree one, and if I have all 3 terms, like a quadratic would have, those trinomials, we can factor it in the form like a quadratic. Okay, but this has to be true. The middle terms, variable, x squared, when I square it, has to give me the first term's variable. In other words, if I have like x squared squared, that does give me x to the fourth. When you raise a power to a power, you multiply. Looks like a y. So if that's true, it is in the form of a quadratic, we would say. So basically, we can treat this like a quadratic. Okay, so we're going to factor it like a quadratic. But instead of x and x in the front here, we're going to need x squared and x squared to get to x to the fourth. Okay, so our setup's a little bit different. To get to x to the fourth, it's going to be x squared and x squared. And we're going to see if it's factorable. The factors, let's see, well, what does this -4 tell me about my signs? It tells me they're opposites. And the factors of 4 that subtract to 3. Factors of 4 that subtract to 3 are 4 and 1. And to add up to -3, the 4 must be negative and the 1 must be positive. Okay, now this problem is actually not completely factored. Over here we have a sum of squares. That does not factor. But we also have a difference of squares, and that does factor. So we can break this one down a little bit further. Here my a value would be x. My b value would be 2. And this factors as x plus 2 times x minus 2. And of course, this guy, even though he didn't factor further, he's still part of my factors, so I don't want to forget him. X squared plus 1. And this would be as factored out as I can make that quartic trinomial. Okay, let's try another one here. Again, it has 3 terms. I'm hoping it's in the form of a quadratic. So as long as this first term's variable, x to the 6th, is x cubed times itself twice. And that is true. X cubed times x cubed, it does give me x to the 6th. So it's in the form of a quadratic. This time, instead of having x or x squared, it's actually going to need to be x cubed times x cubed to get me x to the 6th. Let's see. This positive one tells me they're the same signs. The middle term tells me they're both positive. And the factors of 1 that add up to 2 are 1 and 1. Wow, this problem could get really ugly here. This is a sum of cubes. And this is also a sum of cubes. So to really factor this out, my a value in each of those is 1. My b value, sorry, 1x, which we can really just say is x. And my b value is also 1. So if we follow that sum of cubes pattern, gosh, this is going to get really long and ugly. I'll try to write small, I guess. So we're going to have x plus 1. Then it's a squared, in this case x squared, minus a times b, so minus 1x, plus b squared. And 1 squared is 1. And since there's 2 of these, they're both going to factor the same way. So there's my second one, minus x plus 1. And this is as factored out as we can get it. If you want to, you could try to simplify it by writing like x plus 1 squared, since there was 2 of those times each other, and x squared minus x plus 1 squared. You could try to condense it a little bit like that. Either one of those is fine. This just kind of got ugly because we had a couple sum of cubes. Okay, our last one here. Again, it's got 3 terms. I'm hoping it's in the form of a quadratic, so I check. If I square x to the 4th, do I get x to the 6th? And no, I don't. I would get x to the 8th. And that's not what I have as my first term, so this does not factor. At least not in the ways that I know of yet. So in this one, I would just say it's not factorable, or does not factor. Okay. All right, our last one. If I have 4 terms, and this is really the last one that we're going to have something to help us with, try to break these things down. And you'll see in some upcoming sections, if none of these work, they get kind of ugly and really time consuming. So these are awesome when they work. Okay, so we're going to factor by grouping. And I want to show you something that's going to be a little weird. Let's say if I was going to FOIL this thing out. 2x squared times x is 2x cubed. 2x squared times 3 is 6x squared. 5 times x is 5x, and 5 times 3 is 15. So this is the answer if I FOILed them together. And in fact, when we go to factor this is going to be my answer. Okay, but I want you to see this just for a second, because we're going to kind of do something that looks a little strange, but it makes sense, hopefully, if you see it this way. So remember, when I'm first FOILing this, I'm going to take my 2x squared and multiply it by x. It's going to get multiplied by the x and by the 3. And so it's kind of equivalent to just doing 2x squared times x plus 3, just distributing it to those two terms. Okay, and then adding our result with this 5 times the x and this 5 times the 3. So 5 times the x and the 3. And then we're just combining those like terms. In this case, none of them actually combined, but that's what we would get. So this is equivalent to what we did here, these two factors. And the reason I'm pointing that out is because we're going to get to something where we get to here, and we're going to need to recognize that that is the same, a little darker color, as this. We need to recognize that this really means this, that if I have 2x squared plus 5, both being multiplied by x plus 3, that we can write that as 2x squared plus 5, the quantity, times x plus 3. Okay, but what we're going to need is what's in the parentheses here to match, so that they're both being multiplied by the same thing, and then we can write it as one quantity, 2x squared plus 5 times x plus 3. So we're going to get to this step when we do factoring by grouping, and we're going to need to translate it back into this in the end. Okay. All right, so let's give this a shot. So factoring by grouping is exactly what it sounds like. We're going to group these together. Okay, everybody's going to get a buddy. We're going to pair them up. And typically, you can go first two, last two. So I'm going to group these two together, and then I'm going to group these two together. Okay? What we're going to do is take out the greatest common factor in each. So from this pair, they're both even. I can take out a 2, and I can take out an x squared from both of them. So I'm going to take out my 2x squared, and let's see what that would leave me with when I factor it out of this pair. Dividing that 2 out, I'd get a 1, and I'd be left with 1x. 6x squared, when I divide out my 2x squared, 6 divided by 2 is 3, and x squared divided by x squared is 1. Those basically go away. Okay, so I got x plus 3 is what was left over. Okay, now if factoring by grouping works, I should be able to take out a common factor in this second pair, where what's left in the parentheses matches x plus 3. So obviously looking at these, they don't have an x in common, but they do have a 5. So I'm going to factor out this positive 5, so I'm going to write it as plus 5. When I factor that out, it does leave me with x plus 3. Okay, so going back to what we talked about over here, if I can get what's in these parentheses to match, x plus 3 and x plus 3, that tells me one of my factors is x plus 3. And then these guys on the outside, the 2x squared and the plus 5 is my other factor. So 2x squared plus 5 is my other factor. And I can always double check by foiling these together, kind of like we talked about at the beginning, to see if it really does get me back to the original, and it does. Okay, so we were able to factor by grouping here. Okay, let's try this again on this one a little bit speedier. So again, I'm going to just pair these up kind of first two, last two. We'll keep that negative sign with our 27. So here I don't really have a number I can factor out, but I can factor out an x squared from each. And that would leave me with 3x minus 2. Now remember, I'm going to need what's in the parentheses to match 3x minus 2 over here. Which means I think I'm going to have to take out a negative number. That way I get a positive 3x here. And it looks like 9 is the largest number that goes into both. So we're going to factor out a negative 9. That way I get a positive 3x. Negative 27x divided by negative 9 is positive 3x. And 18 divided by negative 9 is negative 2. And success, we got the insides of our parentheses to match. So 3x minus 2 is one of my factors, and the other factor is what's on the outside here. It's the x squared minus 9. Now in this case, you might have recognized this is a difference of squares, and we could break this down further. We can take out an x plus 3 times x minus 3. Breaking down the x squared minus 9 further, that's a difference of squares, and then 3x minus 2. And this is as completely factored as we can make it. Okay, last example. I know this is running long. All right, let's try this one. Before I even get started, I can already see they all have a common factor. Remember, always look for that greatest common factor first. And I probably should have stressed that with some of these other ones, but I can see it here. Because this guy's got an x, everything has an x, so let's factor that out first. That leaves me with, x cubed plus 3x squared minus 5x minus 15. Okay. And so again, we're going to kind of pair these up. First two and last two, just underlining and squiggly underlining them to group them this time. And from here, I can take out an x squared, and that will leave me with x plus 3 in that group. So remember, over here, I'm going to have to make it match x plus 3. So to change my signs, I think we're going to have to take out a negative number, and it looks like 5 is our common factor. So if I take out a negative 5, I get positive 1x when I divide, and negative 15 divided by negative 5 is positive 3. Nice. Except for that plus sign. Positive 3. So we did get them to match. And that means x plus 3 is a factor. And the guys from the outside here, x squared minus 5 is my other factor. Now that's not really a difference of squares because 5 is not a perfect square, so that doesn't factor anymore. However, I don't want to forget about my x from the beginning that we factored out. He was part of my factors. And this is our completely factored out version